at vector addition with north, south, east, west. And now we're going to look at another method for giving directions. So for this one, all you're going to use is degrees. So here's a little bit of notes there. So if you're given a degree, you always start with 0 degrees. We always have to reference 0 degrees. So how do we do that? Well, here's a silly example with one vector. You travel at 10 meters at 30 degrees. So the way you would set this up is you would start with your protractor. Now you don't necessarily need a protractor. You don't have to draw these things to scale. They can be done freehand, and you're just kind of doing a rough estimate. But I have a protractor here on the board for today. So here's our baseline. Now we're going to pick a starting point. I'm going to put it right there. And this baseline over to the right here is 0 degrees. So we always have to reference 0 degrees when we're doing these directions. So for this single vector, let's see if I can get this to work. So we want a vector of 30 degrees. There. So now we've got a 30-degree vector there. So that would be 10 meters. There's our angle of 30 degrees. Just like the other ones, we can add another vector to this. So if we went 10 meters at, I don't know, 90 degrees, we can go up to 90, add another vector. Now notice, I like how this one does it. What does this blue line here represent? 0 degrees. So we have to start at 0 degrees again. So this is also 0 degrees. And we have our 90-degree angle right there. So when you're adding them, we're always referencing 0 for our original ones. And then our resultant vector would be from the very start to the very end. And we would have to go and figure this out. Now, again, for grade 11, you're only going to do perpendicular vector addition. So there's always going to be a 90 degrees somewhere in this triangle. So for this one here, this example, there's no 90-degree angle, so you won't do anything quite like this. You need to use sine law or cosine law for these ones, and that's grade 12. So here's another quick example. That was an excellent question. Can you ask it again, please?
Sure. I was just wondering if, like, when you look at the degree, if it could be starting from the left side, like 45-degree angle, starting at the left side instead.
No, with these degrees, we always start it from the right-hand side. So 0 is always facing the right-hand side. All right? Very good question. All right, so let's set this question up. So we've got a force of 25 newtons at 45 degrees. So again, I'm going to pick a starting point. Let's say right there. And I'm going to draw an angle. Now I have to have my 0 degrees in there. And we have to go off at about a 45-degree angle. Now again, it doesn't have to be perfect. It doesn't have to be drawn to scale. So that's 45 degrees, and we've got 25 newtons. All right. Then the next one is 135 degrees with a force of 30 newtons. So I should draw this next vector a little bit bigger. Again, doesn't have to be perfectly to scale, but to help yourselves out, you might want to just try and get the relative sizes good. And 135 degrees. Well, where's 135 degrees? Well, there's 90. There's 180. So 135 somewhere in between the two. So we're going to draw it like this. Now, is that where I should put that vector? No, it needs to. If we're doing vector addition, I need to add them head to tail. So I need to place this one at the end of that one there. Okay? Because we can't add our vectors. We know that if something pushes it this way at 25 newtons and something pushes it that way, that we're going to end up going off in that direction somehow. All right? But we don't know, we can't do that. We can't add it properly with this vector over here. So we need to move it over there. That's how we draw proper vector addition. Now where's my angle of 135 degrees? Well, that's where this vector starts, right there. There's 0 degrees again. So my 135 degree angle is right there. Okay? And this is 30 newtons. All right. Now there's something I want to caution you about. There's my resultant vector in the red there. There's a couple things I want to caution you about here. First of all, do we know if this is going straight up and down? No. I've drawn it that way because it's just a rough sketch, but without actually doing the math, I mean, we can kind of look at it and know that which way it's going to kind of lean, but just be careful how you draw things, and don't always take your diagrams as being 100% accurate. Because if you're doing a rough sketch, there's a good chance that you might have messed this up. It could be leaning more towards this direction. It could be leaning more towards that direction. All right? So just make sure that you're not taking these as being 100% accurate. The other thing is, where's my 90-degree angle in this triangle? Killian?
Right there.
Yeah, it's right here. Now, there's a whole bunch of proofs that you could I could show you.
Other one's 45, so it makes sense that.
Yeah, somewhere along here, there's a. If we continue this line, you used to have to do this in grade 9 math. You'd learn how to do all these proofs for, you know, interior opposite angles with 2 parallel lines. There's a whole bunch of proofs that go along with this. The complementary angle to this. You add them together, you're going to get this is 45, this is 45, so therefore it's 90.
Well, yeah, I just actually made that like the first line we did a right triangle.
Mm-hmm.
And I know that the other one's 45, and then 145 plus 15.
Yeah, there's a few different ways you can do it. So, but yeah, that's our 90-degree angle right here. So there's always going to be at least one 90-degree angle in the ones that you do this year. All right. So given that we have a 90-degree angle here, which angle do you think you're going to want to find? Over here or over there? The first one, over here. Because this is where we started, right? You always find the angle, or you usually find the angle by your starting point. And this was our starting point. All right, so I'll give you a minute to do the math there. Okay, so a squared plus b squared square root will give us the magnitude of side x. So what did you get for an answer?
39.
15. Holy, oh, 39.
39.
Wait.
Well, 2 sig figs on both. We'll pretend that this was 2 sig figs. So 39 newtons. Okay, and as far as the angle, 50.2. Now, again, just to remind you all, when you're doing the angles here, going to 1 decimal place would be fine. We're not going to worry about sig figs when it comes to the angle. I want 1 decimal place. And why did I use tan?
Opposite over.
We were given the opposite and the adjacent sides. So you always want to try and do your calculations using given values, not calculated values. So we could have done sine or cos and used x that we calculated to be 39, but we don't know if we maybe made an error or if there's some rounding errors or something like that. So always try and use your given values. Now, when we want to write out the answer, we say that F net is equal to 39 newtons. That's the magnitude. Now, force is a vector quantity, so we also need to have a direction. We figured out this angle to be 50.2 degrees. But Jillian, you were just saying something. Is that what the angle is? Is that the direction?
No, don't you have to add 45 because you're starting from 0 degrees, not from
That's entirely right. We have to add 45 to this angle because we're starting, we have to reference 0 degrees. All right? We went off in that direction there. So how do I, if I'm standing here at the starting point, I have to have a starting point to, which I'm facing. So I'm going to start by facing 0 degrees. So I'm going to start by looking off in this direction here, and you're going to tell me, how far do I need to turn? So how far do I need to turn? Well, I need to go this 45-degree angle first. So 45 plus theta more. So 45 degrees plus that much more. So this little mess here that I've made is how far I need to turn in total. So you need to go 45 degrees plus 50.2 degrees, and you get 95.2 degrees total. So our F net is 39 newtons at 95.2 degrees. That is my direction. There's no north, south, east, west here. This is just taking you and saying, how far do you need to turn? So with north, south, east, west, you have those 4 quadrants, and you use north, south, east, west to kind of give you a direction. You should never, ever, ever, if you're using north, south, east, west, get an angle that's greater than 90. Because between north and east, there's only 90 degrees. Between east and south, there's only 90 degrees. So it wouldn't make much sense if I said, okay, face north, and then turn 130 degrees towards east. Because there's a simpler way to say that, okay? With this one, with this method, where you're only given degrees, we always use 0 as our reference point, as our starting point, and we say, well, how much are we going to turn counterclockwise? Okay? So in this case, we're turning 95.2 degrees counterclockwise. And our resultant vector is actually pointing off a little bit beyond 90. So it would be, if I drew the diagram right, it would be more off in that direction there. Okay? Okay, so here are 10 more practice questions. And now that we've gone over degrees, and we will do more examples of this, obviously, but now that we've gone over degrees, you can do all of these, and you can do questions 4 and 6 from that handout I gave you yesterday. Okay? Now this file here with the 10 questions, I've actually shared it with you through the Google Drive, so you can get it that way, or you can watch the video and pause it, or you can just copy a couple questions down now. It's entirely up to you. Okay. All right. As far as your lab goes, I probably won't be checking the marks on that until Saturday-ish. So if you're looking for a time frame for when it exactly needs to be done, Saturday is probably fine. Have a nice extra long weekend, girls. Okay.